artificial intelligence.
Our first speaker is one of the exceptions who has not only pushed AI to production, has seen it work, has seen it fail, and recovered from it. He has the experience of looking at AI past its hype and has worked on the non-glamorous parts that people don't post about on LinkedIn. He's the perfect person to decipher what AI actually does, how to get from unstructured, chaotic data to actual intelligent, usable, and deterministic systems. So please welcome the VP and head of AI at Leapfrog Technology, Mr. Manu Chatterjee.
All right, can you hear me? Thank you so much. It is really a joy to come to Nepal and to be able to talk and to meet all of you. I'm happy to give this talk on unstructured chaos. It seems maybe a little buzzy, but how we can use AI to do useful things. I work as the VP of AI at Leapfrog Technology. I flew here from San Francisco, so I went from San Francisco to Doha to here, and thank you so much for having me. So a little bit of an agenda. I've split the talk into a few parts. First is kind of defining what is this paradigm shift of AI, and then to kind of pull that together, what's the history of computing that led to this level of AI, and a little bit on LLMs and chats, and then using LLMs to do useful work, and then managing tools and context so that we can get dependable results. So a little bit about me. So I was an electrical analog engineer when I started about 30 years ago, and I really love soldering and putting things together. I think every house should have an oscilloscope, but if they don't, maybe you can experiment with AI. I went to grad school, I did some papers, something called Circuit Reader, which could take a scanned image of a handwritten circuit and convert that into a schematic that could be run on a computer simulation. So my experience with kind of neural networks and things that's from the 90s was, I would say, earlier, but it was a lot of work to get those things to actually happen. I worked at Motorola and Hewlett-Packard and a few other large companies, Palm, and in various roles doing a lot of engineering management, and I've also been the founder of a few startups. So I founded a company called Windowscope, which you've never heard of, because it failed. So there's a lot of experience in trying to raise money, get things to work, and get that put together. Then I founded another company called LampDusk. Now, LampDusk is one of those funny things like, what's a lamp dusk? If you Google LampDusk, you'll get a dusk lamp, which makes a lot more sense. But when you're a geeky co-founder and your other co-founder is also a geeky co-founder, you're like, what's our technology? Well, we use the lamp stack, and we're using desktop software. I know, we'll just call it LampDusk. Everybody will get that is, and we'll just focus on this, and then when we get the marketing guy in, he'll fix the name. But what actually happens is, once you put some brand equity in a name, it just stays that way. And ultimately, that company was acquired by Palm, as in Palm Pilot. And we had this niche product called WebVM, which allowed you to run web applications offline. And that evolved into another thing called WebOS. If you buy an LG television today, that is the direct lineage to WebOS. After that, I left and I did some consulting, and I was at, co-founded another company called Trends in AI. That actually read the internet. We read about 80,000 sources of news every single day. We had a whole Python cloud in AWS. We would read the Wall Street Journal, we would read New York Times, we would read pieces of Twitter. And in Trends.int, with that, we built a knowledge graph, and that knowledge graph could allow you to ask questions like, did Hurricane Andrew affect IBM? And because we knew what Hurricane Andrew was, and we knew where IBM had facilities, we could see the path. And so you get interesting results, and so we sold a data feed to financial companies. And that was ultimately acquired by a company called Interos. Now you think, wow, this guy's killed it, he's sold 2 startups, he must be a gajillionaire. Actually, my special talent is making money for other people. So here we are. And finally today, after some consulting, I am really having joy with the Leapfrog team. So there are a few Leapfroggers around, talk to them as well, and let's begin our journey. So AI. There's so much talk about AI. Our first two speakers talked about AI. What is AI? What makes it different than previous computer revolutions? And I was chewing on this as I was kind of building the other parts of the talk, and then I thought, you know, I really want to ground this. And I came up with kind of this, I hope, simple metaphor. Pre the internet, humans were the goal setters, humans the information, the planning. The work was done by humans, and the scale was limited by whatever humans could do. Then we got the search era. Let's say the Google 2000, that kind of thing. Humans were still the goal setters, but you would search the internet and it could get you a wealth of information, like I want to travel to Nepal. Maybe I should not call a travel agent, I should Google that or use Travelocity or something like that. It'll get me results. But I still had to do the work. I still had to go to the website and book things. It just helped me narrow down the scope. So much faster, game changer for those of us who went to the library, but still there was something more. Now we're kind of in this beginning of the AI era. Humans are the goal setters. But now computers can do the planning, the ChatGPT. And the big difference is that the work is done by computers. It becomes delegation that couldn't be done before. I can tell the computer to do it, and hopefully it does the right thing. Ideally, I could say, book my travel, and then the nice thing is, if it's a good assistant, I could say, change my travel, keep it up to date, just like an assistant would. So that's the area that we're going to talk about today. Of course, maybe what comes next? Humans? Maybe there's computers are the goal setters, computers do the information, computers do the work. Look, Ma, no hands. So for those of us who are thinking about what the future ethical implications of AI are, not my talk, but we have some speakers today talking about that, some really good things to think about. Okay, so a lot of harm to AI. I would say there was a manual era, mechanical leverage. Programming languages were about human time efficiency. So if you look at mechanical switches to program ENIAC, to machine language, to Fortran, to C, in each generation, you get further away from the machine, and you can describe things more compactly. If you look at a scripting language like Python, and you just use like the two curly braces to have a dictionary, if you look under the covers, if you have the point of view of a C programmer or a something programmer, there could be thousands of lines of code for those two curly braces. And when we get to AI, we're saying, you know what? We can replace that with clear English grammar, or Nepali grammar, or Chinese grammar, or whatever it is, we're kind of expressing an intent. But that intent comes at a cost. While it is much faster, there is less precision. And that leads us into a lot of interesting places. So to frame kind of why that is, I want to take a brief tour into some things that came before. The first chatbot that really kind of, I'll say worked, was something called Eliza. It was actually an experiment from the 1960s. It just looked for keywords, and it would respond with something called the doctor script. So if you've ever gone to a psychologist or something, then they say, how do you feel? Maybe this would be better. And Eliza was like that too. He said, hey, are you real? Well, what do you think? Hey, I'm not feeling so well. Oh, why is that? They would just kind of have these canned phrases. But people who played with Eliza were just amazed by how human-like it felt. But of course, if you went off the handful of things that he could actually talk about and that ambiguous grammar that it would always close, it wasn't real AI. But as computers got better, we started to be able to use computers to accomplish useful tasks, especially in areas of manufacturing and other kinds of financial decisions. We could take our knowledge, spend a lot of human time, and organize it into rules. Effectively, if-then statements or switch statements, and say, if this condition is met, then we have some sensors, and it would parse through all that data, and it would make a decision, and it could do things. So for banking, for a lot of industries, this expert-based rule system stuff works today very well, and it's super dependable. But it is domain bound. It is stable in the best of worlds, work for proven use cases, but
but it doesn't allow you to just do it. You can't just ask for it. Then as machines got more powerful, we were able to start the paradigm of machine learning. So now we take lots of data and we'd say, hey, machine, here's an example input, here's an example output, and another one, and a few thousand more, maybe a few million more, maybe 100 million more, and eventually we would figure out some mapping from the input to the output. And we could give those output labels. So we say, these are cats, these are dogs, here's 100 pictures, here's 1,000 pictures, and eventually it could do that for us. We didn't have to do any programming. The machine was doing the job of learning the mapping, whereas in the expert system, we gave it the mapping and said, just follow the rules. So label-driven, very important. Real world wins, but the paradigm is shifting. And another thing is there's this idea of neuron, artificial neuron. You'll see that come a bit later. But neurons in the machine learning sense are still very different from human neurons. They tend to take a bunch of signals in and make an output. In human neurons, there's time. There's a big element. There's state that's in the neuron. So there's a lot of other things that are still there, but this generation of AI was very useful. And then in fall of 2022, ChatGPT happened. Now, for those of us who were working on different parts of AI or just pattern recognition or machine learning, LLMs have been around, the attention is all you need paper had come out, there were a lot of other pieces of perception that were working. But ChatGPT did something very important, which is it brought this idea of interfacing with the computer to the masses. The interaction changed. It was a natural interaction, and you could get understandable results without any kind of knowledge of expert systems or coding or anything like that. So let's talk about large language models. They handle loose amounts of data. You can give it a text or notes, and they kind of do runtime coding. Your prompt plus some data gives you some kind of useful result. One system can do the summarization, it can do the extraction, it can do planning. This is what really changed from code time interpretation to runtime interpretation. But the LLM is not a machine that looks up stuff in a database and recalls it. It is a trained guessing machine, for lack of better words. It learns patterns and it inferences that. Even when it remembers things really well, it is going through the sequence of things it's learned and figuring out the plausible results. And if it's read trillions of documents, it's pretty darn likely it'll get things that are commonly discussed very well. So if you're talking about recent history, if you're talking about well-traveled things, it will almost seem like it remembers. But there is no idea of internal truth. There's only ideas of making sure that it emulates that idea of the pattern that it learned. And so this can lead to kind of interesting challenges because it looks like it knows what it's doing, but it might not. And if you see this in a domain where you're truly an expert, like let's say you're an expert in calculus or something. Wow, there's a change. It can talk about calculus in an incredible level of detail. It can tell you about the history of calculus, it can tell you about calculus operators, it can tell you about all kinds of things. But it might not be able to do calculus, at least not in any way that you would trust. And this is very important because it comes out with such surety because it can quote like Leibniz and Euler and all these people. It can show little things. But what happens is as humans, if you run into a person in real life who can talk like that about calculus, they really know calculus. There is zero chance you can run into a person who can talk about calculus and not do it.
So this creates an interesting cognitive dissonance about when the machine is truly accurate and when it's not. Hallucinations. So hallucination is really a term that comes from an outsider's point of view of what the machine is doing. It didn't get that right. It just made that up. But if we go back to how the LLM works, in some ways everything's a hallucination. What it's really doing is just predicting, given your inputs and your data, what a logical output would be. And if you think about that, a hallucination, if it makes something up, is that logical based on what it knows and was trained on? Quite probably. Is it truthful? Possibly not. It might be, it might not be. So truth, or any kind of objective measure, or reliability, has to come from outside of the core LLM response, because inherently it is always just a statistical guessing machine. But hallucinations are not a simple bug, because they're inherent to design, and the solution, or the hallucination, is also the same mechanism that allows it to generate its useful output. When you say correct this email, it's never seen that email before, any more than I have, and now it's correcting it, so it's actually doing useful work based on its token prediction mechanism. So the hallucination is very much interwoven with the whole way of the value that the LLM provides. And so this creates unique challenges when we start thinking about reliable systems. Now, LLMs have some cousins that are also very useful, or maybe they're even part of LLMs. Multimodal models allow LLMs to do things that you could never do with some of the earlier AIs, which is they can also read pictures, they can handle audio, and they can actually handle custom signal information, like from various sensors. Because you can break those kinds of informatic pieces into tokens or sequences of numbers just as you can text from any language. And if you train and blend that all together, the model can look at an image just like it can look at text. And this means that it can actually see an image if you give it that, see text if you give it that, and still operate in the same domain, like rewrite that email, and based on this text, also give me a summary. It can do audio. It can listen to audio, and it can project what that was said and into useful information as well. And we can also take LLMs and their cousins diffusion models and generate outputs. So many of you have probably used the image generators that can generate like funny pictures of cats and dogs, or Nano Banana, which can then take an image and make that into something else. These are different kinds of large language models that can take a seed and an intent, and they can build out a new image or new audio. If you look at some of the recent music, you can actually take old music, run it through new models that can generate audio, and change the genre. So you can change from rap music to soul music and keep the lyrics. This is incredible stuff, and it comes with many implications, but it is part of the power of utilizing the generative power, the LLM power, the hallucination power of an LLM. All right, if we move from what LLMs are wired to do and what they can do, let's talk about getting them to do the thing we want them to do. Usually what we do is we have a context which is open loop. We say, take this email and clean it up. Take this email and tell my boss I should be given a raise. Your email doesn't say that, it generates that. But whatever it spits out, you should read that, because who knows what it might actually say. Manu, you know, he's, I don't know, I read some of the other stuff Manu's doing, maybe he shouldn't get a raise. You don't know what it's going to say. So it's important that you make sure that you are in the process of looping with that. And that's very natural. If you look at ChatGPT, you'll say, okay, here I am, I got some output. No, more like this, less like that. You are the person, the feedback loop, the computer, if you will, that's telling the worker how to clean it up. And that works great for small pieces of work, or for work where I don't need a lot of scale. And it also works when you need to do one-off jobs. So if I say, take this block of text and reformat it as a table, as a computer scientist, I might have wanted to code a script to do that, but I don't need to do that now. I can just have the LLM to do that. And the LLM might even use tools to do that. And we'll get to that in a second. But what if the text that you want to give it, the context you need to give it, is so huge that you couldn't possibly give it to an LLM? Well, why couldn't you give it to an LLM? All LLMs today have a limited amount of memory that they can operate on at runtime, called the context window. When ChatGPT came out, that context window was stunningly short. It's like 8K, grew to 32K. The largest models now are in the 128K to 2 million token range. A token is typically a group of characters, maybe 3 to 7, depending on the embedding, but what they are is around maybe 1 million to 5 million characters at max, which is not that many if you say, you know what, I'm going to take all the documents in my company and have it an HR bot that tells you whether you're following policy or not. I'm going to take all the users in this huge database and tell me which one is the one who's most likely to fulfill a certain role. Now it's just much larger than the LLM can really handle at one time, so we need to have augmented procedures. And the most common one is to use something called vector databases in RAG. So rather than say, okay, I don't know what to do, maybe I should have the LLM do a bunch of things and see if it can find each person, before we even do that, we take the whole database of people, we can give it to something called a chunker and a tokenizer, we give it to a vector database, it cuts it up into pieces, and now what happens is it uses the same internal mechanism that the LLM does for understanding internally, and it can find the matching people to some query. So you say, okay, tell me all the people who are most likely to be C++ programmers in my company. It's got all the resumes, it's read all of them, it's put them in a vector database. The vector database says, here's my best guesses, which are really vector matches, and then it feeds that into the context of an LLM, and it can return that. But it's still open loop. The LLM says, okay, I took the best guesses, I generated the outputs, and here's the guys who probably match. And then you can condition that to format that in a list or in a recommendation. So it's still open loop, but it's now allowed the LLM to have access to a much larger context than could be possible with an LLM alone. To improve that, we start to add tools. So companion to RAG is the idea that we can hook the LLM up to other tools so it can do useful work. For those of you who use coding tools like Claude Code, you see this all the time. For those of you who use Notebook LM, other of the ChatGPT project things, it's using a tool to search the internet, and it gets a result. It uses tools to use the file system, gets a result. It uses tools to do structured actions. So all these things can be done by tools, but the problem is that with simple tools, you have to integrate each tool into the LLM's calling cycle. This can take a lot of energy. So to make the tools more general, we move something to Model Context Protocol. So Model Context Protocol is a way of making tools simple enough, generic enough, that I can attach any tool to an LLM, and it can say, okay, I've got the list of all the tools, you gave me 100 tools, I read through all of them, and then when I want to use tool 5, the file system, and tool 17, the database lookup, it interacts with that tool through the MCP protocol, and there's a dialogue that goes back and forth, and says, okay, I know how to call that tool, I know how to get the result, and then with that result, I will then run the next loop in your process and hopefully get you the result that you actually want from the LLM. So there's a lot of advantage with MCP because you can connect almost any service, but there are some detriments because, remember that context window? The MCP dialogue and handshake can take a lot of time in terms of tokens. And so as a result, the LLM can start to lose track of where it's at. So you need to be in a position where you can start to manage the goal intent above the level of individual LLM calls. And that leads us to agents and agentic workflows. So with agents, we can say, okay, we have a group of things that should be done in one task, and another task, and another task. We have some kind of flow idea. And what we want to do is we want to say, okay, take in the document, read it and find all of the first name, last name, billing number, account number. If that's good, pass it to the next thing. File it with the claims processor, follow these rules. Remember those rules from before? They're still useful. And take that to the next thing because we can keep moving through the progression of tasks. Now, one of the things that's kind of confusing in the grammar of agents, how we talk about them is, you don't really talk about a task in terms of developing an agent. You talk about it in terms of the steps that needs to be done and how those steps should be handled accurately. And so I kind of say, as we're looking at agents, how to do agentic workflows, if you have a human you want to give that, you say, I'm not going to build a human. You say, I give a human this task and the list of things that need to be done, and then the employee works on that workflow task. So a lot of the challenges with getting agentic workflows right is having the right mindset about what is a task, what are the rules that need to be followed for each version of that task, and then making sure that that's repeatable and reliable. There are a lot of things like agents.md or other kinds of files where you can describe what needs to be done. Equally important is enforcement of the rules. If you're an open source programmer, you have no shortage of rules to follow. You have to make sure you check out the code. You want to create a branch that has the right name. There's a test-driven methodology you want to follow. There's all these procedures that are not really part of the task. They're the boilerplate of making sure that the task is done robustly. So the key thing with making agentic workflows actually reliable is to integrate the idea of the task that needs to be done with the rules that also need to be followed. And there are many different ways to do that. And that leads us kind of to reliability. If the LLM is ultimately not fundamentally trustworthy, that means that reliability has to be enforced onto the agentic system from the outside, from ground references of truth, from ground references of rules, from other techniques to detect when things are unavailable to rules, techniques to see whether they're on track. So LLM as a judge, take the output of one LLM, give another LLM and say, does this look reasonable? Because if you're processing text, there's probably no easy way to make a rule for it. Design over prompting, system level thinking about how things are tied together over how things are actually done at the LLM level. In some ways, the LLM becomes a much smaller and smaller but important piece. It handles areas where you need to have unstructured input and have a result or a classification. And the outside becomes more important. The database, the rule enforcement, these kinds of systematic logging and tools. And in some ways, I think as we look at LLMs advancing, we can say, we can just give the LLM and load up with tools and see what happens. But you would never do that with an employee. You wouldn't say, here's all the tools, go figure out what your work is. You would say, this is what we need done, this is the way we do it. If you find a better way, tell me, but do it the same way every time. And so the LLM becomes more like a CPU, and we're building the computer around it. So, where is AI at today? There are a lot of things that we can do with these agentic workflows by having those rules and that enforcement and the external pieces. Intelligent document processing, decision support at scale, workflow automation of many kinds, insurance claims, healthcare, voice and call centers. If you call a voice or call center, maybe not this moment, but certainly in the near future, it's not just that it can handle out-of-order input, like maybe it's, oh, Mr. Chatterjee, you called back. Oh, I see you called in July, and your computer, you did this stuff. Does it still work? Like, it won't go through all those questions because it can remember automatically. No call center agent could do that, no matter how good prompting scripts and screens you give it. So there are things that will come to, fuzzy processing. I'm still speaking. Maybe I switch to Bengali and then back to English. To the LLM, that's fine, right? I could switch to Chinese and back. Well, maybe not me, but these are things where that ability to combine the input processing power of the LLM with the ability to have agentic workflows will be incredibly changing. So in closing, we are seeing a defining shift of AI where the information of search and execution and all these systems are coming together to task level delegation, engineered trust, human in the loop, and huge operational impact. Search scaled knowledge. AI scales work. Thank you very much.